Hello everyone. In this video, we will quickly review what are Bernoulli differential equations and how we solve them, and then I'll do some examples for the solving of this family of differential equations. First of all, Bernoulli differential equation is a nonlinear differential equation, first order, and it has this form that y prime plus a multiple of y equals to multiple of a power of y. So recall that the linear differential equation was of this form, y prime plus, I'll write lowercase p for this, equals to qx. Okay, and the nonlinearity of the Bernoulli differential equation exactly coming from this power of y, and the reason that we said that n must not be 0 or 1, that's because that's how we get nonlinear differential equation. Well, the general strategy is that we know a substitution called Bernoulli substitution, using which we can turn our nonlinear differential equation into a linear differential equation, and then we know how to solve linear differential equation. That's the strategy. But let's see what are the details of this. So first thing is that you have to recognize Bernoulli differential equation. Remember, it was like y prime capital Px times y equals to capital Qx times y to the power n. So you have to know three things. What is this, what is that, and what is that n? Okay? When you know that this Bernoulli, then you can go ahead and use the Bernoulli substitution. What is Bernoulli substitution? We define this new variable u to be equal to y to the power 1 minus the n, which introduce the nonlinearity to our equation. Then we transfer our equation to an equation for new variable u. If you do all the steps correctly, you will see that your equation will turn into this equation, derivative of y times a multiple plus a multiple of u equals, there is now no power of u there. So this is a linear differential equation. And to be precise, this is lowercase px and lowercase qx. Now you can go ahead, solve this linear differential equation, integrating factor, and then find the solution. And then at the end, what you solve here will be for u, then you have to turn it back in terms of y. Okay, so recognize it, apply the fix the Bernoulli substitution, apply the Bernoulli substitution, solve the linear one, and then substitute back the original variable. Okay, so let's see this in some examples. Here you see that, okay, my differential equation is of this form, and you right away should see that the capital Px is -1, capital Qx is e to the power -x, and specifically the nonlinearity comes from that n, which is equal to 2. It is Bernoulli, for sure we can see that. Now we use the Bernoulli substitution. Bernoulli substitution, which is, well, new variable u equals to y to the power 1 minus n. And here is 2, so it will be 1 to to the power negative y to the power negative 1. In other words, u is equal to 1 over y. Now I want to rewrite this equation in terms of an equation for u. Okay, I know how to change y to u based on this recipe given here. How about y prime? The relation between y prime and u prime is given by differentiating this thing. So if you differentiate this, let me just go one more step, differentiate. So this will be du dx. I'm applying chain rule here. It will be negative 1 over y squared dy dx. This tells us what is the relation between dy dx or u prime and y prime. I have to multiply y prime by this term to write it as u prime. So to be able to do that, I will multiply everything by negative 1 over y squared. So that will give me negative 1 over y squared y prime minus negative 1 over y squared times y, and negative 1 over y squared times e to the power negative x e to the power 2. You see, this is the magic of Bernoulli substitution. The right hand side, all the terms in terms of y will cancel out. There won't be any y left for the right hand side. In the left hand side, this term here, y over y squared is 1 over y. So, and there's this minus. This guy, I know what is this. Look at our substitution here. 1 over y is u. So this guy is going to be u here. The right hand side, there is no y, so I'm not worried about anything there. But this guy there is exactly what I have just found for du dx, or you just x u prime. So this is how we turn our nonlinear to linear. So this is called this is now linear differential equation. Well, we know that now I have the coefficient of u here. This is lowercase px1. The right hand side, this is qx. So I have all the terms there. I can go ahead and solve it. So integrating factor. Which will give me ix is equal to e to the power integral of px dx. And this is e to the power integral of 1 dx, which is e to the power x. Then the solution, or the general solution here, is ux equals to 1 over integrating factor, integral of qx. Integral of qx dx times integrating factor, which is ex, plus c. And as you can see, this is 1 over ex, integral of negative 1 dx plus c. And well, that will solve my differential equation. This is e to the power negative x times integral of negative 1 is minus x plus c. That's nice. We turned our nonlinear differential equation to a linear one. We solved it. Now here is the last step. Substitute back y. So you remember that the substitution was what u equal to 1 over y. So that means that y is equal to 1 over u. So this is my u. So it is e to the power negative x minus x plus c. And I can take that negative e to the power negative x upstairs and write it as this guy. So my solution for our original differential equation is e to the power x, let me just write c minus x. And that's what we were looking for. However, there were this initial condition there that now I have to apply and fix the constant c. So let me push this one a little bit lower. So I know that y at 0 is 1, and that means that 1 is equal to e to the power 0 c minus 0. So that means that 1 is equal to 1 over c. That gives me what is the value of c. So combining these two, now I have the solution for my initial value differential equation given by this. There is a point here that all the steps that I have done here, it turns out that if you know how Bernoulli substitution changes your Bernoulli differential equation to linear differential equation, these can be done easily just by this. So if you set u equal to y 1 minus n, then the differential equation will be of the form d u dx plus 1 minus n, the original capital Px u equals to 1 minus n qx. So you need either to know this is what will happen after the substitution is done, or you have to be able to apply these steps for each question separately. Let me do another example here. So this is my differential equation. I have to be a little bit careful here because I need to do something. The first thing is I'm dividing whole equation by 1 over t squared. So that will give me this. And that is, you see the nonlinear term, which is, well, fixing n. This is capital P, t in this case, because t is my differential, my independent variable, and capital qt, which is 4 over t squared. So that shows that this is Bernoulli, the differential equation. And now I can apply Bernoulli substitution. And while here u is going to be y to the power 1 minus n, and that is this guy. Well, I will apply all these steps. So du dt is going to be negative 2y to the power 3 dy dt. So if I apply everything, if I multiply everything by negative 2 over y cubed, I will get, let me just write these ones. 2ty and then minus ty cubed 4 over t squared y cubed. As I said before, this is the magic that y's will cancel out on the right hand side, and on the left hand side they will cancel out so that you get a good u there. So this will turn my differential equation to u prime. This is u prime. Then you multiply these two plus 4 over t u. 1 over y squared is u, and the right hand side is minus 8 over t squared. That's it. Remember that I said if you know the substitution, it will turn everything to this form: 1 minus n, the original capital T, U, and 1 minus n, the original capital Q. And here you see this was the Q. Now I multiply it 1 minus 3, which is negative 2, multiply negative 2. That's what is my new Q, T, and this is exactly the original PT multiplied by negative 2, which is 4. This is my new PT. So this is a linear differential equation, and now you can find integrating factor e to the power integral of 4 over t dt. This is e to the power 4 ln absolute value of t, and this is e to the power ln of, since this is t to the power 4, absolute value will just give us the same. I don't need to take the absolute value. And then oops, I'm using now properties of inverse property of e and ln. That's t to the power 4. Then ut is going to be 1 over t to the power 4 integral of qt minus 8 times t over t squared times t to the power 4 dt plus c. And this is 1 over t to the power 4. This is minus 8 integral of t squared, which is t to the power 3 over 3 plus c. That is solution for my variable u. Now I want to substitute back. So from this, you remember that u was 1 over y2. That means that y squared is going to be 1 over u, and that means that y is equal to 1 over square root of u. So I'll apply those steps. It will be y 1 over root u t, which will give me 1 over t to the power 4 minus 8 over 3t cubed plus c. And well, if I do some work, this t to the power 4, it will come out from the square root, and it will give me t squared. But since it is in the denominator of denominator, I can put it in the numerator, and this is c minus 8 over 3t to the power 3. Well, we found the general solution for y, and now it's time to apply the initial condition. Y at 1 is root 3, so I will use black one there. Y at 1 is root 3, so that means that root 3 is equal to 1 to the power 3 root c minus 8 over 3 1 to the power 3. And if I square both sides and inverse, so c minus 8 over 3 is equal to 1 over 3. From there, c is equal to 1 over 3 plus 8 over 3, which is 9 over 3, and that gives me just 3. So applying those, I turn this to the final solution for y, which is t squared over root 3 minus 8 over 3t to the power 3. And that's how we found or solved that Bernoulli differential equation. As a last example, I won't complete this one. There's only one point here that I want to mention. Well, the variables are a little bit different. Now we are working with u and t. If I divide the whole equation by t times u squared, then you'll get du dt plus u cubed over u squared. That will give me just u 1 over t there equals to 1 over t u to the power negative 2. This is Bernoulli, n is negative 2. And then you go ahead, apply the substitution you like. So here, since already we have u there, I will use v at t is equal to, or just v equals to u to the power 1 minus n, so u to the power 3. V is u to the power 3. Then if you turn your differential equation for v, it will be dv over dt plus 3 times this, 3 times the original p, which is 1 over t, times 3. That's 1 minus n. Remember, 1 minus n will be multiplied there. 1 minus n, here it is 3, will be multiplied to this one. And there won't be any v in the right answer. So this is the linear differential equation, and I'll leave it for you to solve this one and turn it back to the original variable u in this case. Okay, so the rest I'm leaving it for you, but I'm hoping that with the examples done before now, you know how to deal with Bernoulli differential